Welcome to Problem Solving in STEM, Example 2 by Conceptual Calculus. In the first video of this series, we saw a method for solving problems in STEM. In this video, we see another example of how that method can be used. The example concerns interest on an investment. The solution uses Excel. I will explain every step of the Excel work for students who may not have very much experience with Excel. Here is our example. Fred and Wilma want to save for Pebbles' education. They have found a college savings account that pays 5% annual interest, compounded continuously. They plan to deposit the same amount in the account every year on her birthday, starting the day she is born, with the last deposit on her 17th birthday. On her 18th birthday, they want to have $20,000 in the account. How much should they deposit each year? First, we organize the given information, starting by writing down the facts. The interest compounds continuously at an annual interest rate of 5%. Fred and Wilma will deposit the same amount every year. 18 years after the first deposit, the account should contain $20,000. We want all information in the same system of units. We already have that. We need a variable name for any quantity that is unknown. I'm going to use P for the amount they deposit each year. Next, we make sure we know what we are trying to find. We want to know how much they should deposit each year. That means we want to find the value of P. In some problems, a diagram is very helpful, but I don't see a use for one here. So we move on to assembling relevant known information. Do we know anything about continuously compounded interest? You've probably seen this in pre-calculus, but if you don't remember it, then you can always Google it. The equation describing continuously compounded interest is A equals P times e to the power RT. P is the amount deposited, R is the annual interest rate as a decimal, and T is the time in years. Together they give A, which is the amount in the account after T years. We have all the information we need to plan our solution process. Our formula, A equals P times e to the power RT, works for a single deposit made at one specific time. Our problem involves 18 deposits made at different times. This means it will help to break this problem up. I'm going to use the formula to find out what Fred and Wilma get from each one of the deposits, and then add the results for all 18 deposits. We should also consider what technology we want to use. Excel can be very helpful for repetitive calculations. Now we are ready to carry out the plan and solve the problem. As we do that, we need to make sure our work is well organized and labeled, so that someone later could read and make sense of it, and also so that we don't lose track of what we are doing while we are doing it. Open an Excel workbook and follow along with what I do. I will explain every step. Before we put any numbers into Excel, we label the cells so that we can keep track of what those numbers mean. First, we need a place to put the interest rate. Expressed as a decimal, 5% is 0.05. Then I want a column to keep track of how old Pebbles is when each of these deposits are made. The first deposit is made the day she is born, so she is 0 years old. That header is a bit long for its column, so I'm going to change the formatting on the header row. Click on the left end to highlight the row, and then go into the Home tab and pull down the Alignment menu. Select Wrap Text. I also want to center her age in the column. Back to the Alignment menu, and this time I select Center. That's nice. You don't have to format things exactly the way I do, but you should know how the formatting works, and you should try to make your work neat and readable. Now, I want to know how many years the deposit will be in the account. It will come out when she turns 18, so it is there for 18 years minus her age at the time the deposit is made. This is the first calculation in this problem. We will be doing several calculations, so we need to know how it works. A cell in which you do a calculation is called a formula cell. The first thing you type in a formula cell is an equals sign. Then you put in the rest of your calculation. I want 18 minus her age. So I type 18 minus, and then I click on the cell containing her age. Now it says 18 minus C2. C2 means the cell in column C and row 2. That's where her age is. Now our formula cell shows 18, which is how many years the first deposit will be in the account. The next column will show the amount of money in the account when Pebbles turns 18, based on the deposit made when she was born. I want this header to extend over 2 columns. I select the first cell, click, and drag over to the cell in the next column, and then go back to the alignment menu. This time I select Merge Cells. Now the header is in one large cell made from merging the 2 original cells. It's not as tall this way, so the first row does not need to be so tall. I go to the left and put my cursor on the dividing line between the first and second rows. Then I double-click. That adjusts the height of the top row so that it is just large enough to fit the things that are in it. Below this new header, I want to put the amount in the account. A is P times e to the power RT. I don't have a value for P, though. That's what we're trying to find. I'm going to type that in as P times, using an asterisk for times. This does not cause Excel to perform a multiplication. It's just for humans to read, to better understand what the numbers mean. I do have enough information to calculate e to the power RT, though. The function to get e to the power of something is exp. exp is short for exponential. This is a formula cell, so I start with an equals sign. Then I type exp and an open parenthesis. Next, I click on what I want to put in there. I want the interest rate, which is in cell A2. Then I type an asterisk for multiplication, and then the number of years, which is in cell E2. Close the parentheses and hit Enter. Now I can see the result. On Pebbles' 18th birthday, the deposit that was made the day she was born will be worth almost 2.5 times its original amount. I want to neaten this a bit. I select the cell containing the P, go back to the alignment menu, and select Right Justified. That moves the contents to the right end of the cell. Then I select the cell containing the number and left justify it. Now the two are right next to each other, which is how multiplication is usually written. So, we have the first row, with everything nicely formatted, to tell us about the deposit that is made the day Pebbles is born. What happens next year? Pebbles is a year older, of course. Go to the next cell down in the age column. Type an equals sign, click on the cell above, and then type +1. In this row, her age is 1 more than it was before. Select the cell for the number of years the deposit is in the account. Mouse over to the lower right corner. When you see the cursor turn into a plus sign, click and drag down to the cell below. Now that cell contains 17. The deposit made on Pebbles' first birthday will be in the account for 17 years. Let's look closely at how that works. The upper cell contains 18 minus C2, where C2 is 2 cells to the left of that formula cell. The next cell down contains 18 minus C3 because C3 is 2 cells to the left of that formula cell. This is called relative addressing. Instead of always looking back at cell C2 to get her age, each formula cell looks 2 cells to its own left. This continues to work as we extend the table down to add more rows. Now, let's try that trick again. Select the 2 cells containing P times 2.4596. Mouse to the lower right corner and look for the plus sign. When you see it, click and drag down 1 row. Well, that's not what we want. That says the amount in the account is 1 times the deposit, meaning the deposit has not gained any interest in 17 years. What went wrong? If we look at the upper one, which worked correctly, we see that it uses information from two other cells, A2 and E2. Now we look at the next row down and see that it adjusted, just like last time. It uses information from cells A3 and E3. But there's nothing in A3. The interest rate is in A2. I do want it to use relative addressing and adjust through the table to get the number of years. But I want it to always get the interest rate from the same cell. I have to tell it not to adjust that row. Go back to the formula in cell H2 and put a $sign to the left of the 2 in A2. The 2 is the row number. The $sign tells it not to change that. As we go down the table, it will always get the interest rate from row 2. This change doesn't make any difference to the values shown in cell H2, but when we copy this down to H3, now we get what we wanted. The deposit did gain interest during those 17 years. Not quite as much as the first deposit gained in 18 years, but close. That is what we expected to find. I'm zooming out now so that we can make a larger table. Select row 3 and copy it down several lines. I didn't get quite as far as I wanted, so I'll extend it a bit more. Oops, too far. I'll select the extra lines and hit delete. Now we have a table that shows every deposit from the day Pebbles was born to her 17th birthday. For each one, we can see how much it increased between the day it was deposited and her 18th birthday. The earlier ones gained more interest because they were in the account longer. The later ones didn't gain as much. We want to find the total. As usual, type in a label to help you keep track of what you are doing. The amounts are all P times something, so the total will also be P times something. To get that something, we need a new formula. Type an equals sign, the word sum, S-U-M, and parentheses. With your cursor between the parentheses, click and drag to select all the numbers in column H all the way back to the top row. Then hit Enter. I'll zoom in on that a bit. The total we have in the account is P times 29.9279. What is it supposed to be? Fred and Wilma want to have $20,000. That's the desired amount. Now we can find the value of P. I'll label it P equals, and in the next cell, type our last formula. We know that P times 29.9279 is 20,000. So P equals 20,000, which is in cell I-21, divided by 29.9279, which is in cell H-21. Fred and Wilma need to deposit $668.27 every year to meet their goal. I'm zooming out to demonstrate a bit more formatting. I want to put a box around my answer. Select those two cells and go up to the Font menu. There are a lot of options for cell borders. I'm going to use a thick outline. Now let's look at the entire table at once. Suppose Fred and Wilma see that result and decide they can come up with more than $668.27 a year. They ask us how much they would need to deposit each year to end up with $30,000. We just change the $20,000 to $30,000, and immediately we have our result. To end up with $30,000, they would need to deposit a bit more than $1,000 a year. I'm taking that back to $20,000. Next, we can check the effective interest rate. If they could get 6% instead of 5%, then they could reduce their annual deposit to $598.92. That's about $70 less each year to get the same result of $20,000 in the end. I hope you can see that doing this on Excel works better than trying to do the same calculations on a hand calculator. It would take so many calculations that you would be very likely to make a mistake along the way. Even if you didn't, you would have only the answer to the question about 5% and $20,000. To find out about 6% or $30,000, you would have to do it all over again. We are nearly ready to take our answer back to Fred and Wilma. For 5% interest and a final balance of $20,000, they need to deposit $668.27 every year. Now we think about that. First, we want to make sure the result we found is what we were trying to find. we were trying to find the value of p in dollars. That is what we did find, so that's good. We came up with a total number of dollars, so our units are good. Is our value of p about the right size to be reasonable here? Well, the total of all the deposits is 18 times 668.27, which is a little over $12,000. We expect the interest to add to that, so a final account balance of $20,000 does not seem unrealistic for the number of years that some of this money was in the account. Finally, we state the result in terms of the question. We were asked how much money Fred and Wilma should deposit. So that's the question we answer. Fred and Wilma should deposit $668.27 into Pebble's account every year. That's the end of this example. For other examples using this method to solve problems, please see later videos in this series. They don't all use Excel. For each problem, we use the technology that is helpful for that problem. Thank you for watching Problem Solving in STEM, Example 2 by Conceptual Calculus.